Hello everyone, welcome to topic 9.3, Gibbs free energy and thermodynamic favorability. By the end of this, you should be able to explain whether a physical or a chemical process is thermodynamically favored based on an evaluation of Gibbs free energy, or delta G. And there's a bunch of breakdowns for this, so read them at your leisure. So Gibbs free energy, G, describes the energy available in a system that can be used to do work. By calculating the Gibbs free energy, we can determine if the system has enough energy available to undergo the process, and thereby determine if the reaction will take place. We describe reactions that can take place as thermodynamically favorable or spontaneous. As we have seen before, there are two forces, enthalpy and entropy, that determine if a reaction takes place, and we need to account for both. If a reaction is thermodynamically favorable, we know that it will take place. However, it does not tell us how fast the reaction will be. For example, some thermodynamically favored reactions are very slow, such as the rusting of iron. I lost my spot. Rusting of iron. This is an example of a reaction that is said to be under kinetic control. We have to look at the kinetics of the reaction to determine if that rate will determine the rate of the reaction. Okay, so it'll happen on its own. That is what thermodynamically favorable means. It'll go. You don't need to put energy in. You don't need to use a catalyst to lower the activation energy. It'll go. However, kinetic control says that the rate, it may go so slow that it'll take forever, right? So kinetic control, the rate is going to change that and control that one. So enthalpy describes the energy required or released in a chemical or physical process. We know that exothermic processes, ones that release energy, are favorable, where delta H is negative. Entropy is the amount of energy as a function of temperature that is not available for work because it is lost in molecular disorder. We know from the second law of thermodynamics that in an isolated system, a sample will arrive at a state of thermodynamic equilibrium where entropy is highest. Processes that move towards greater entropy are favored. So a positive or negative delta H and a positive delta S tell us that it is thermodynamically favored. Okay, if the flip sign, so a positive delta H and a negative delta S, that is thermodynamically unfavored. Okay, but if they match, so if we have both of them negative or both of them positive, we have to do a little bit more digging, and we're going to get into that here in a second. In some cases, it is necessary to consider both enthalpy and entropy to determine if a process is favored. Consider the process of freezing water at standard pressure. When water freezes, it releases energy, so the delta H is negative, so this is favorable. But the particles have more order when they are solid, so the delta S is negative and unfavorable. We know that when the temperature is less than 0 degrees Celsius, water spontaneously freezes, so the Gibbs free energy is negative. But if the temperature is over 0 degrees Celsius, the water doesn't spontaneously freeze. Therefore, the Gibbs free energy is positive. Okay, so it's temperature based. So when they are both negative or they are both positive, it is going to be temperature based. Likewise, we can look at what happens when sodium nitrate is placed into water. The dissolution process for sodium nitrate is endothermic. So the process absorbs heat from the water, so delta H is positive and unfavorable. However, the ions are more disordered when they are dissolved, thus the entropy of the solution has increased, so delta S is positive and thus favorable. We know that the standard temperature of the process is spontaneous at standard temperature, so 298 Kelvin or 25 degrees Celsius. This means that it is thermodynamically favorable and that delta G is negative. So the temperature is high enough to make this process favorable. From these two examples, we can see that there are many factors to consider in determining if a reaction is thermodynamically favorable. In the last lesson, we saw that for spontaneous processes, the entropy of the universe is equal to the sum of the entropy of the system and the entropy of the surroundings, and that is generally positive for a thermodynamically favorable or spontaneous process. We learned to calculate the entropy of a system in 9.2. Now we need to calculate the entropy change of the surroundings. To do this, we look at what causes entropy to change in a reaction. When an exothermic reaction takes place, heat is transferred to the surroundings. The surroundings in turn increase in entropy due to the added energy. When the temperature of the surroundings is already high, there is less change in entropy when it absorbs heat. And when the temperature is low, there is more change in entropy as the surroundings absorb heat. This means that the entropy of the surroundings is proportional to the enthalpy of, and inversely proportional to the temperature Kelvin, leading to this following proof that, looks like magic, so keep going. You do not need to be able to derive it, but they're showing you that it is logical. There is math behind it, and thus, from this wonderful math bit, we got this equation that we're going to get to here in a second. So, magical math gives us this bit. If the term minus T delta S of the universe is less than 0, the reaction is said to be thermodynamically unfavorable, as it describes the amount of available or free energy that can do work. It is named for Josiah Willard Gibbs, where negative T delta S universe is G, or Gibbs free energy, and therefore is calculated as follows. And it gives us this equation. For reactions that are thermodynamically favorable, Gibbs free energy is less than 0 or negative. Okay. Always check your units, where enthalpy, or delta H, is typically provided in kilojoules per mole, and entropy is typically provided in joules per mole Kelvin. So be sure to convert them to the same unit, and it's usually kilojoules before subtracting. So if you have a number of joules per mole Kelvin when you are doing your math, I like to just tack on that 1 kilojoule is 1,000 joules to remind myself I need to divide this term by 1,000 to get kilojoules, so that way my math works out. So you got to make sure your units for energy, or joules, match each other, and typically we express it in kilojoules. We know that if temperature increases, then the entropy of the system increases. So an increase in temperature would magnify the entropy. Since we know that entropy is the energy that is unavailable for useful work, it is the energy lost to the disorder of the system. So we subtract the T delta S term from the enthalpy of reaction. That gives us the energy that is available. So energy in the system, energy that can't do squat, take the difference between the two, and this is the energy that can do something. Okay? So delta H and delta S values are provided in a table of thermodynamic data, so you won't be asked to memorize those. They'll be provided to you either in the problem or they are in the back of your textbook that you can look them up. Delta G is also back there. So when the entropy is favorable, delta S is positive, and the enthalpy is favorable, where delta H is negative, then the reaction will always be thermodynamically favorable, having delta G as negative. When the entropy is unfavorable, well, and vice versa, right? Unfavorable, delta S is negative, enthalpy is unfavorable, positive, then the reaction will never be thermodynamically favorable, and so Gibbs free energy is positive. In general, the temperature conditions for a process to be thermodynamically favorable, where delta G is less than 0, can be predicted from the signs of delta H and delta S, as shown in the table below. So when we have this one is negative and this one's positive, it's always this one's positive, this one's negative, it's never this one's positive and positive only when it's high temperature, and negative, negative only when it's low temperature. I think I said that right. Yes, I did. Okay, and so here we're going to explain that below. So we only need to calculate the delta G of reaction to determine thermodynamically favorable if one of the terms is unfavorable. So like in the third row, the delta H is unfavorable, and in the fourth row, the delta S is unfavorable. So at high temperatures, the entropy term is favorable. The T delta S term will be greater than the unfavorable delta H term, and thus favorable entropy will dictate the thermodynamic favorability. And at low temperatures, if the entropy term is unfavorable and the T delta S term will be smaller than the favorable delta H term, and thus the favorable enthalpy will dictate thermodynamic favorability. We can calculate Gibbs free energy for a reaction when all the reactants and products are in their standard state. Standard state is a reference point for all substances, and it measures gases at 1 atmosphere of pressure, solutions at 1 molarity, and the temperature at 298 Kelvin. To indicate that the values are at standard state, there's a circle that is used as a superscript as shown in these. The standard state, please remember, differs from STP, which is where standard state measurements are at 298 Kelvin, so the temperatures will differ. The temperatures differ, right? So 298 Kelvin for standard state, and standard temperature and pressure for gases is 273 Kelvin, so those are different. In order to calculate Gibbs free energy for a reaction, we can compare the Gibbs free energies for the formation of products with the Gibbs free energies for the formation of reactants. These values are tabulated in an appendix in the back of your textbook, and you can just go there and look them up. A lot of the times these will be given to you, so you don't need to memorize them. They'll be given to you, but you may, for like classwork and stuff, have to look in a textbook. So here's the equation. Remember, or notice that this is, very similar if we just subbed out H for these, or, we just talked about S in a recent. So they're all very similar equations because they're all state functions, meaning we don't care about the path, just where we started, so our reactants, and where we finished, products. Okay, so let's look at an example. The decomposition of hydrogen peroxide, H2O2, occurs slowly at room temperature according to the following reaction. Predict the sign for delta G and justify your answer. So here, if we're reading closely, the decomposition occurs slowly at room temperature. It occurs without any outside force. So that tells me that this is spontaneous, because it occurs on its own. So that means that delta G has to be less than 0 or negative for a process to be spontaneous. Okay, now we're going to predict the sign for delta S. Well, we look at this, we go from aqueous to a liquid and a gas. Well, we know gases have the highest entropy value. So that means that we are increasing in overall entropy. So that means that our delta S term is positive, and this is because, or so, let's write these the same. So greater than 0 or positive, right? And this is because gas is produced, and it has the greatest entropy, so entropy is increasing. Okay, so now let's look at this we do. Consider the reaction given below, calculate the value for delta G, and determine if the reaction is thermodynamically favorable at 298 Kelvin. So remember, delta G, it's giving me delta G values, so I'm going to take the delta G for the reaction, and I'm going to do my products minus my reactants, first multiplying by their coefficients. So our products, so we have 2 water, so I'm going to do 2 times water, which was negative 237.2, plus 4 times carbon dioxide, which is negative 394.4, plus 2 nitrogen. And then I'm going to subtract my reactants. So here we go. 4 Hydrogen cyanide is 121, and 5 oxygen. Uh-oh, I ran out of room. Oh, that's just 0. So, hey, that fits. Woohoo! Okay. So, calculators are your best friend. So, shove this into a calculator and you should get negative 200 or 2,536 kilojoules per mole. And we know it's kilojoules per mole because those are the units given. And since we're only adding, the units don't change. And so because it is negative, we know that this is spontaneous. Or the AP preferred term is thermodynamically. Yeah, had to sound that out. Favorable. Right, that's the preferred AP term. It's thermodynamically favorable because you're differentiating between the energy of the system and the rate. So thermodynamics versus kinetics. Okay, so given these examples, remember we went over a couple extra equations and you are going to use them, and we did not do an example for them in the notes section. So make sure you're using those, but we're good at our algebra. So complete the you do, check your work, and thank you for tuning in.